Okay, so this video is going to go over your lab prep for our hydrogen peroxide analysis. I'm not going to read all of this that's on the slide right now. You can go through and read it. I'm just going to kind of overview what we're actually doing. So when you buy hydrogen peroxide at a drugstore like CVS, Walgreens, etc., the hydrogen peroxide that you usually buy is a 3% hydrogen peroxide, which means it's 3% hydrogen peroxide, 97% water, okay? Now here's the thing with hydrogen peroxide though, is it tends to break down pretty readily. That's why it's in that brown bottle, right? Because if it's exposed to light, it tends to break down into water faster. So that's why hydrogen peroxide is usually in brown bottles. So what we're going to do in this lab is we're going to do a titration, and I'm going to use a drugstore hydrogen peroxide to see how close it actually is to that 3% of hydrogen peroxide. So I guess I have to click, sorry. So let's talk about the balanced chemical reaction here, okay? Because this is what we're going to need in order to analyze how much hydrogen peroxide is in that drugstore hydrogen peroxide container. So this balanced chemical equation, we won't learn this until second semester. So I went ahead and did the balanced chemical reaction for you. It's just important that you understand what's happening during the course of the chemical reaction. So if I was to calculate manganese oxidation number here in this MnO4, oh, first of all, let me say one thing. You're used to hearing me say potassium permanganate, but you're like, Stoser, there's no potassium there. Correct, because it's an ionic compound. And what we learned in this chapter is that when we have spectator ions, they cancel. So potassium becomes a spectator ion because it's just K plus on the reactant side and K plus on the product side. So we're just going to ignore it because it doesn't do any chemistry. So back to what I was saying. So if I was to take the oxidation number of manganese here, it would calculate out to be +7. And then as I go over here to the product side, it turns into +2, which means that during the process of this oxidation reduction reaction, manganese is gaining 5 electrons because it's going from +5 to +2, okay? Now, with that specific electron change, since it's changing its chemical composition, we're changing the color, okay? So when we first start, you'll see this very bright purple color, and during the course of the titration, it's gonna move to be colorless, so clear, transparent, okay? But we don't wanna go all the way clear because then we're gonna miss our endpoint, okay? So our endpoint is gonna be light pink because as we add, that purple is gonna turn more and more like pink, and then right before it turns clear is the color that we're shooting for. So it's like the same color as the phenolphthalein. So when we do our data analysis, it's important that we come back to this balanced chemical equation. For every 1 mole of potassium permanganate, we will use 8 hydrogens, which is just from the H2O2. Okay, so I'm gonna kind of walk, again, I'm not gonna read all this, it's very wordy, but I'm gonna kind of pull out what I deemed important, and this is how your lab should be prepped. So by reading this, I saw that the purpose of this lab is to analyze H2O2 in a common drugstore solution by titrating it with potassium permanganate. The concepts that we're drawing on from chapter 4 are oxidation reduction reactions, titration, equivalence point, and standardization. Okay, now the one thing that I want to talk about is procedure because this is a lot, okay? This is a lot. And we've already done a titration. So since we already have a titration in our lab notebook, we can be very brief with this titration because we can refer to the titration we did before. So I'm gonna kind of show you how I do that. Okay, so the first step that they're telling you is that you're obtaining 75 milliliters of potassium permanganate standard solution, blah, 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 blah. Shorten it. We're going 75 milliliters KMNO4 at a molarity of 0.025 molar, record. Next thing, prep by rinsing out, just like we did with sodium hydroxide. We're gonna place the burette under the stand. We're gonna fill the burette, and then we're gonna record the initial volume, just like we did with sodium hydroxide. After that is when we're gonna prep our hydrogen peroxide solution. So we're going to measure out 1 milliliter of hydrogen peroxide into a 125 milliliter Erlenmeyer flask. And then we're going to add about 20 milliliters of distilled water. So just like when we did the sodium hydroxide titration, it doesn't matter how much water I add because I have that 1 milliliter of H2O2. And then we have to, and I don't want you to worry too much about this because this is past the scope of what y'all need to know, but we have to make this solution acidic in order for the reaction to go. So we're going to add 10 milliliters of 3 molar sulfuric acid. And then we're going to start titrating. So you're going to titrate initially 5 to 8 milliliters to watch what's happening with the color change. And then you're going to continue to titrate until you get that light pink color. And then the endpoint's reached once you see that light pink color. You're going to record the final volume and then complete 2 more trials. Sorry, I should probably go back so you can pause and look at that. Okay, and then the last thing you have to have prepped is your data table. It looks very similar to the one that we did with sodium hydroxide, except we don't have grams of hydrogen peroxide because we're just using 1 milliliter for each one. And we'll talk about how to do that analysis after we do the lab. So you need to record the molarity of KMNO4. It doesn't change across the 3 trials, but what you do have to do is the initial, final, and then the difference. Okay, and that's it for your lab prep. Thank you.